Hi and welcome. In this video lecture we are going to derive the step response of second order overdamped system. We know that the equation, the closed loop transfer function for the second order system, which is C of s divided by R of s is equal to omega n square divided by s square plus 2 eta omega n s plus omega n square. So here we are going to take the step response. Okay, so step response, we know that step signal we are going to given to that second order system, and we are going to check how the response will be there likewise. So this is the step input signal we are giving to the system. So step signal is somewhat constant with respect to time. So we are assuming that R of t is the step signal. So the magnitude is 1. Yes, of course we are applying unit step input to the system. So the system response will be somewhat exponential in nature, which means we know that the response for the critically damped system. Okay, so critically damped system means exactly equal to eta equal to 1. Okay, so this is over damped system. So for over damped system, eta value is greater than 1. So it may be 1.5 or it may be 2 or it may be 3, 4, likewise. The system response is completely dying. While increasing the value of the eta greater than 1, the system response is very poor, and that is why we are saying this is over damped system. So which means the damping we are applying to the system is somewhat exceeding the main requirement. That is what we are called as over damped system. Okay, let's derive the equation now. So R of t is 1, which means R of s is nothing but 1 by s. Okay, this is some kind of Laplace domain. We are representing the step input. So first step, so we are going to in this derivation also we are not supposed to substitute any value for eta, because this is somewhat greater than 1. Okay, so let eta be the eta itself, and we know that formula. Okay, so we know that formula like any second order equation like a x square plus bx plus c. Okay, so you can find the root value, the value of x, with the help of this formula, minus b plus or minus the whole root of b square minus 4ac divided by 2a. This is the standard formula, we already know. It is very familiar to us. Let me substitute this formula in this denominator section. We can find the value of s. We can find the value of poles. Okay, so s equal to minus b in this equation is 2 eta omega n. Okay, 2 eta omega n plus or minus root of b square. B square is nothing but 4 eta square omega n square minus 4 into 1 into c value is omega n square. Okay, divided by 2 into a. A value is 1. Sorry. So s equal to minus 2 eta omega n plus or minus the whole root of 4 eta square omega n square minus 4 omega n square divided by 2. So within the root itself 4 omega n square and 4 omega n square is we are having, and if you are taking 4 omega n square as common and we are taking out of the root, we will get minus 2 omega eta omega n plus or minus 2 omega n the whole root of eta square minus 1 divided by 2. So s equal to minus eta omega n plus or minus omega n root of eta square minus 1. Okay. So actually this equation going to be separated into two parts, s into s plus 1, s plus s1 and s plus s2. Okay, so the roots is nothing but minus s1 minus s2, is it not? So this is this equation is having two values, okay, plus or minus. So minus eta omega n plus omega n root of eta square 1 is one solution, and one more solution is minus eta omega n minus omega n root of eta square minus 1 is one more solution. So s equal to minus s1 minus s2. So s1 is equal to minus of this value, I mean the first solution. So this is s1 we are assuming. So minus s1 is nothing but minus into minus plus eta omega n. So plus we are considering plus into minus minus omega n root of eta square minus 1. Similarly s2 is equal to we are considering s2 is nothing but minus eta omega n minus omega n root of eta square minus 1. So multiply by minus, this minus minus will get cancelled, eta omega n minus into minus plus we are getting. So this is the value of s1 and s2. Okay, the roots of this equation we are calculating with the help of this formula, and which is s1 and s2. This is what we are getting. So now we need to rewrite the closed loop equation such as what? C of s divided by R of s is equal to omega n square whole divided by what? S plus s1 into s plus s2. So throughout the derivation we are not going to use the whole polynomial. Instead of that I will simply use s1 and s2. Okay. So we need to find out the step response, is it not? So response is nothing but output. So output is here. So bring the R of s at right side. So okay, C of s is equal to R of s into omega n square the whole divided by s plus s1 s plus s2. We know that this is the step response derivation. So R of s for step input, R of s is 1 by s, already we discussed here. Okay. So let's substitute the value of R of s here. We are getting the step response immediately, 1 by s into omega n square divided by s plus s1 s plus s2. So this is the step response of the second order overdamped system. Okay. But we are studying about time response analysis, so of course we need to represent the equation in terms of time domain. So in order to convert this equation, this S domain equation into time domain equation, so we need to take inverse Laplace transform. Okay, so let we take the before taking the inverse Laplace transform, we need to take partial fraction for this equation. Okay, so take partial fraction. Okay, it will be C of s equal to omega n square the whole divided by s into s plus s1 s plus s2 is equal to, this is actually the first case, so we can separate this equation into three parts, like a by s plus b by s into s plus 1, c by s plus s2. B by S plus S1, C by S plus S2. We need to find out the value of A, B, C. Substitute the value of A, B, C here. We can easily take the inverse Laplace. So, how to find the value of A, B and C? Simply, as first step, initially we need to take LCM, is it not? S into S plus S1, S plus S2 is equal to, if we take LCM over the polynomial, see, S into S plus S1, okay, S plus S2, I am taking LCM over here, so A into S plus S1, S plus S2, similarly B into S plus S2 plus C into S plus S1. I think this is equilibrium. These two equations are equilibrium. Yes. Let's cancel out these two denominator terms. We are getting the equation like omega n square is equal to A into so and so, B into so and so, and C into so and so. So initially put S equal to 0 in this equation. Okay, you are getting omega n square is equal to A into S1 S2 plus B into 0 plus C into 0. Okay, so A equation, A is nothing but omega n square divided by S1 into S2. So this is what we are getting for the coefficient A. Okay, so we need to represent in terms of S1 and S2 value. Okay, let's substitute the value of S1 S2 here. Okay, so A is equal to omega n square the whole divided by eta omega n minus omega n root of eta square minus 1 into eta omega n plus omega n root of eta square minus 1. Okay, I think it is correct. Okay, fine. This is similar to, okay, A plus B into A minus B, which is A square minus B square, is it not? I think it is visible now. Okay. A plus B into A minus B is equal to A square minus B square. So consider it is an A, B, A minus B into A plus B. Okay, so we can change the denominator term as like as follow: A square eta square omega n square minus omega n square. If you are taking square for this term, the term will be eta square minus 1. Okay, omega n square divided by eta square omega n square minus omega n square eta square, minus into minus plus omega n square. Okay, this two term will get cancelled, and also if you are cancel out this term, A value will be 1. Okay, so this A value is 1. Then this is the equation what we are in the need to substitute the value of S now. So put S equal to minus S1. Okay, we want to find out the value of B, so put S value as minus S1. Okay, so in this equation, if you are substituting S value as minus S1, omega n square is equal to, okay, omega n square is equal to, can you check out here, A into 0, okay, minus S1 plus S1, the whole term will get cancel out, and B into minus S1, we are substituting S1 instead of S. Okay, so we are getting P of minus S1 into minus S1 plus S2 plus C of 0. Okay, here also S1 term is available, so 0. So what we are getting, the value of B is equal to omega n square divided by minus S1 into minus S1 plus S2. Okay, keep the value, keep the sign. Okay, don't take the minus to the numerator. Keep the minus at the numerator itself. Okay, let me substitute the value of C. This is the polynomial for B coefficient we are getting, and in this equation itself we need to substitute the value of S1 and S2. We already calculated during the starting of the derivation. Let we substitute the value of S1 and S2 here. Okay, so B is equal to, I think it is visible, yeah, omega n square divided by minus S1. Okay, minus S1 is nothing but minus of this term, is it not? So minus eta omega n minus omega n root of omega n, eta square minus 1. Similarly, minus S1 plus S2. Okay, so the same minus S1 has to be repeated here, minus omega n root of eta square minus 1 plus S2 plus S2. Okay, we need to write the same equation here. So eta omega n plus omega n root of eta square minus 1. Wait, if you are substituting minus S1 means this term will get one minus sign and this minus will be converted into plus sign. Okay, see, now minus eta omega n plus eta omega n get cancelled. Okay, so what is the remaining term we are getting? Omega n square divided by minus eta omega n plus omega n root of eta square minus 1 into omega n, the same term, a plus a is 2a, so 2 omega n root of eta square minus 1. Okay, so we are not able to simplify after this step, so again convert the same polynomial into minus S1. See, this is minus S1, is it not? So convert the b term is equal to omega n square divided by minus S1 into 2 eta omega n root of eta square minus 1. So we can bring this minus sign in the numerator itself, and also we can cancel out 1 omega n from numerator and as well as the denominator. So remaining thing we are having, which is minus omega n divided by 2 root of eta square minus 1 into 1 by S1 we are getting. Okay, so B equal to, okay, so this is the value of B we are getting from this step, which is, okay, B is equal to minus omega n divided by 2 root of eta square minus 1 into 1 by S1. Just we are separating the root value as one side and other things are other side. Likewise, we are separating in this equation. So fine, B is over now. So find the value of C. So in this equation we need to substitute. Initially we have substituted S as 0 and minus S1. So see, 0, if you are substituting 0 you can get A value. If you are substituting minus S1 you are getting B value. So let's substitute S equal to minus S2. Okay, so put S equal to minus S2. Okay, we can get the value of C. Okay, so let's take this equation and substitute S equal to minus S2. So omega n square is equal to, so A of 0 is not, so because this is having one S2 term, So minus s2 plus s2 0, so a of 0 plus b of 0. Obviously we are having s2 term in b coefficient side, plus c of minus s2 into minus s2 plus s1. Okay, fine. We are getting c equation as c equal to omega n square whole divided by minus s2 plus s1. Okay, so similar to the b equation. Okay, so kindly compare these two equations, omega n square, minus s1 minus s2. Okay, so minus s1 and minus s2, minus s2 s1. Likewise, so this is similar to the b equation. So if you are substituting the value of s1 and s2, you will get the equation similar to the b equation, which means you will get minus omega n divided by 2 root of eta square minus 1 into 1 by s2, what we are going to get. Okay, let me substitute the value of s1 s2 in this equation. Okay, let me try. See, this is what we are going to solve now. Okay, so in this equation we are going to substitute the value of s1 and s2. C equal to omega n square whole divided by minus s2. So s2 is here, so minus s2 means minus eta omega n minus omega n root of eta square minus 1. Okay, into minus s2, the same term, eta omega n minus omega n root of eta square minus 1. Okay, plus s1, eta omega n minus omega n root of eta square minus 1. Okay, so in this equation minus eta omega n plus eta omega n get cancelled. So C is equal to omega n square whole divided by minus eta omega n minus omega n root of eta square minus 1 into minus omega n minus omega n we are having. Okay, so we are getting minus 2 omega n root of eta square minus 1 in the numerator term. Okay, so C is equal to, we are going to replace this term by minus s2, omega n square divided by minus s2, right, minus 2 omega n root of eta square minus 1. So this minus will get cancelled. This omega n and 1 omega n at the numerator will get cancelled. We are getting the C equation as omega n divided by 2 into root of eta square minus 1 into 1 by s2. This is what we are getting as the C value. Okay, see, similar to B equation, so minus sign here, plus sign here, s1 is available, here s2 is available. Sorry, come back to B and C equations, both are something like that, mirror effect here we can see in B and C equation. Okay, so you can see, I think you can see the three values of the coefficients, I think A, B, C. Okay, let's substitute the value of A, B, C in this equation. Okay, so now C of S equal to A 1 by S plus B value is, we are getting minus omega n. Okay, no problem, minus omega n divided by 2 root of eta square minus 1 into 1 by s1 into 1 by s plus s1. This is B value. plus c value c value we are going to substitute now in this place. Omega n divided by 2 eta square, 2 into root of eta square minus 1 into 1 by s2, 1 by s plus s2. Okay, so we can take some term as common. See, omega n 2 eta square, likewise we can take the value of 1 by s minus omega n divided by 2 root of eta square minus 1 term as common from these two terms. So we are taking minus, we are taking minus omega n by 2 root of eta square minus 1 as common. Okay, so here plus 1 by s1 into 1 by s plus s1. So here one more minus will come, s2 into 1 by s plus s2. Okay, this is the response equation is in S domain after taking partial fraction. Now it is ready for taking inverse Laplace transform. So take inverse Laplace transform now. For this equation I am going to take inverse Laplace transform. So Lap inverse of C of s is C of t. This is what we need, is it not? Time response. Lap inverse of, these are all the important formulas, okay, important terms. 1 by s equal to 1. Okay, so lap inverse of 1 by s plus a equal to e power minus a t. Okay, these are all the very important formulas we need here. Okay, now write the time response equation. C of t is equal to 1 minus, these are all not relevant to time responses, is it not? Omega n natural frequency, eta damping ratio, these are all some constant values. Okay, it is not actually a variable, it is actually a constant values. So if you are taking Laplace transform means there is no change over that. So let's keep the same as here, omega n divided by 2 root of eta square minus 1. Inside the bracket 1 by s1 will be 1 by s1. Why 1 by s1? For 1 by s1 term, if you are taking inverse Laplace means there is no change, because kindly check the root value. See the s1 value, what are the parts of s1 value? S1 and s2, both s1 and s2 we are having only eta, omega n term. Eta is damping ratio, constant. Omega n is natural frequency, somewhat constant term. So for constant terms you are taking Laplace transform means there is no more changes. So Laplace transforms can only taken for, inverse Laplace transform only taken for s domains. Okay, so 1 by s1 will be 1 by s1 into, in this place wherever we are having s term, it is only applicable for inverse Laplace transform. So this is 1 by s plus s1. So whatever may be the constant term added with that or multiplied with that s domain term, so it will be same here. So 1 by s plus s1, this is similar to here. So e power minus s1 t minus 1 by s2 is 1 by s2, because we already seen, is it not? S2 is having eta and omega n only. So these are all constant terms. So take the 1 by s2 and keep it 1 by s2 itself, and this is similar to this equation. So e power minus s2 t. Okay, so this is the time response. Okay, this is the time response of what? A overdamped system. If you are applying unit step input to the second order overdamped system, the system response like following the polynomial expressions. Okay, so the system response already we drawn during the starting of this derivation class. So see, if you are keep increasing the value of damping ratio, the system response will be poor. So this is similar to overperforming. Okay, so if you are taking actions for controlling the controlling the output at the set point value, actually you are doing overperformance. Okay, so your damping system is controlling the output. Okay, so that is why we are plotting this response. So this is C of t, black curve is C of t, red color curve is unit step input. So this is the quite derivation for second order over damped system response. Thank you.